I mean, if you just did it alpha 0, alpha 1, alpha 0, it's okay. I mean, that's not bad. It's open-ended, so I'm not expecting one particular answer. I'm just saying how I did it.
I think there's a unique solution that way, though, since there's 3 equations and 2 unknowns.
For which?
Keeping it alpha 0, alpha 1, alpha 0.
Oh yeah, absolutely. You know, there is no unique solution. You're just gonna pick. Essentially, what you're gonna do is pick some other value for the. You just by trial and error, you're gonna pick a certain frequency to be the frequency that the filter zeroes out. Let me just open my, why are we not opening? Open. Right, so here's my part D. I take, so my filter, so I take the H1 filter is the one that I created from the, where is it? That's the one I created from the low-pass filter. That's the one that gets rid of the 10K. And then I did another filter, that H3, that I got from filtering out the 20K. And then I convolve them together. And then, so now that's my new filter that filters out both of the unwanted frequencies. So if I run this, let's just let it go for a minute. Okay, so, right, so here's my combined filter. And you can see that, okay, so the frequency axis is in terms of omega, so, but you can see that this is probably what corresponds to 10K, and that's what corresponds to 20K. So those both get filtered out. And the 1K is the point that corresponds to a filter gain of 1. So it works out all right. Was that it? Yeah? Yeah, exactly. It should work out proportionally. Yeah, I'll buy that. Right.
It's like 6.28 times about 1.5 span. Just 2.6.28.
Well, we could do even better than that, right? We could, just to get you comfortable with the fact that we don't even have to guess, when I go to create the plot, so right now I'm plotting it versus omega. So if I divide that by pi, and I multiply that by, I know pi should correspond to half my sampling frequency. Is that correct? Right? So if I take omega, divide it by pi, and now I should, and multiply it by my sampling, half my sampling frequency. So let's do like this, or rather we'll divide it by 2 pi and multiply it by the sampling frequency, which was, I think I have a variable for that. What do I call it? Fs. Alright, so Fs times. Alright, let's run it. Uh-oh, did I make it worse? I don't know. No. Oh, curious. What did I do wrong? Well, anyway, I'm not going to debug this in front of you, but that should have worked right off the bat. Let me just take one last hack. If I go back to omega, it works fine. And if I plot that, if I take omega, I divide it by pi, and I multiply it by Fs over 2, all right, I'll sort that out later. All right, well, anyway, I'm not going to worry about it. Oh, yes, 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 yes. Thank you. Thank you. That's the problem. Right. There it is. Good catch. So now this is times 10 to the fourth. So that's 10K and that's 20K. Okay, so it worked out fine. Good eye. I was saved. Good. All right, any other questions about the homework? I'll put the solutions on Blackboard tomorrow, especially the second problem. I know the second problem confused some of you. The point of the second problem was not to be a signal processing problem. It's just a MATLAB issue. And MATLAB generally works a lot faster when you avoid things like for loops and while loops. You should always, if you can, try to write your code using using matrix operations when possible. And usually if you're good about it, anything that's got a repeated operation that happens over and over again, you can often just write it in terms of one line of, or a couple lines of matrix code so that you don't need to have a loop. It tends to make things go a lot faster. So I don't want to dwell on it now, but definitely look at the solutions when I put them up tomorrow.
We want to create a n cross n matrix. So in that case, for developing the matrix, we have to use a for loop.
No?
Dynamically define a matrix.
All right, well, let's say you want a matrix of ones that's, okay, so let's say, for example, I give you H equals 1, 2, 3, 4, 5. All right, and now I want to create another matrix that's got H for the row. It's got, let's say, 6 rows, or 10 rows, let's say, and each row equals that. All right, so now I'm going to do... Yeah, but H is, so in the example of the homework, H would be the...
No, in that case, H is fixed, meaning vector is fixed, but the transformation matrix has to be created dynamically.
Watch this. If I take, so there's a built-in MATLAB function called ones, right? So let's say I want 10 rows and 1 column of ones. So now I take that and I multiply by my original value of H. Instantly, in one line of code, I've created a new matrix with my original one in the rows, and then 10 copies of that, each one in its own row. That's just by doing the matrix multiplication. If you do that matrix multiply, where you multiply a column of ones by a row of whatever, that's what you wind up with, and MATLAB did the work for you. And that was the sort of trick that I was trying to get people to exploit in the second problem. So if you write out what all the equations look like for the Fourier transform, you see there's a pattern, right? So, you know, it's always, if you write it in a matrix form, you know, H of 0 equals something plus something plus something plus something. H of 1 equals something plus something plus something plus something. So you wind up with a grid, and there's different terms that are multiplied together in each individual term, and those terms go in a pattern. So you exploit matrix multiplications like this to create that pattern, and then instead of repeating the same thing for each line, now you've got the whole matrix in one go. So anyway, like I said, I don't want to dwell too much on it, but look at the solutions, and if it still doesn't make sense, you know, shoot me an email. But you should be able to pick, using this as a starting point, you should be able to see the, you know, to work from this to the answer. All right, let's, just because I don't want to get behind and it's somehow already, are those clocks not the same? Is that why I'm confused? Here I was thinking we started early. I just looked down at my watch and it's 6:20. I'm wondering how we already got here. Okay, well clearly we need to hurry. What I'd like to do is just take a quick look at today's reading focus questions. And so today's lecture is sort of divided into 2 parts. Oh, today's discussion. So the first half of the discussion is talking about anti-aliasing filters. And the reason we have to talk about anti-aliasing filters is because that's sort of your link between the analog domain and the digital domain. I don't really care if you know how to build them out of circuit parts. We're just talking about the theory of how they get designed, why they get designed, what the trade-offs are. Just painting it in broad strokes so that just because it's an important part of that overall process. And then once we discuss that, we'll discuss the discrete Fourier transform, which is sort of the digital little brother of the discrete time Fourier transform. And we'll look at some interesting properties of that. So let me just pull up the figure from the book that I asked you to look at. All right, so well, that's not very good, is it? Zoom 100%. Can everyone see that? Is that too cruddy? I'll tell you what's what. I'm sorry? You think? All right. So this is your sort of typical low-pass filter, and it's in the digital. Sorry, this is in the analog domain. So essentially, what you're saying is, you build an anti-aliasing filter because you want to get rid of the high frequencies before you sample. If you don't get rid of the high frequencies, you alias. So this we know. So your typical low-pass filter, you've got a pass band and a stop band. And within the pass band, you define something called the ripple. So you say, okay, well, I'm okay with my pass band, with the amplitude changing a little bit within the pass band. You get to tell it how much. And then you also get to specify the same thing for the stop band, right? In your stop band, you might be willing to say, it doesn't have to be 0. I'm willing to have a little bit of energy come through in my stop band frequencies. But obviously, the more restrictive your filter is, the more restrictive your requirements are, the more difficult it is to build your filter. So the basic building block is the filter order. So the greater the order of the filter, physically, the more of it there is to build. So that's like more resistors, more capacitors, more whatever it is. There's more parts to the filter in designing it. So going purely for intuition now, I was going down the list and I was asking you, all right, so let's start with the stop band frequency. So let's start with this picture, and let's say that in order to build a filter that satisfies everything here, that I need to have a filter of order n. So it could be, let's say, a fifth order filter, whatever. So now I want to increase my stop band. So let's say now I'm going to keep everything the same, but I just want to increase the frequency of the stop band. So increase it. So is that going to require a filter of a greater or a smaller order? Smaller. Why smaller?
Because we are relaxing our conditions. We are allowing more flexibility.
Yeah. Right. There's a couple ways of thinking about it. Right. In essence, for all of these, the rule of thumb is that the more restrictive you are, then the higher the order of the filter is. The less restrictive you are, then you can get away with a lower order filter, something that's not quite as fancy. So in this case, if you increase S, now you're essentially making a less restrictive filter. In other words, so one of the properties they talked about in the book was this value of K, which was the ratio between omega S and omega P. And essentially you're saying, you have to transition somehow from the pass band to the stop band. And if these are really close together, then that transition has to happen very quickly. That requires a much higher order filter. Whereas if they're much more spread apart, that transition can happen over more frequency, so it's a less restrictive filter. So yeah, absolutely. If you increase omega S, then you have a less restrictive filter. So your order goes down. So using that logic, you can just buzz down the list and make a pretty good answer for each of these. So what happens if omega p is decreased? Same thing, it's less restrictive. Right. Yeah, exactly. If you decrease omega p, now you've increased your transition band. And because you increase your transition band, it's easier to go from the one to the other. Okay. If I decrease omega s, more restrictive. But exactly. What if I decrease epsilon? Right. So epsilon is this guy over here. Does that show? Yeah. If I decrease epsilon, do I have more ripple or less ripple? Well, let's answer that question first. Smaller epsilon.
Yeah, more ripple. Less the lower level will go up.
You say more ripple? You're saying less ripple. For smaller epsilon. All right, well, if epsilon is 0, right, that's the smallest epsilon you could have, right? If epsilon is 0, then how big is your ripple? No ripple. 0. Okay, so as epsilon gets bigger, you have more ripple. So now I'm telling you, let's decrease epsilon. So that should decrease our ripple. Right? That means a more restrictive filter, a higher order. Well, that was complicated. How about A? What if we increase A? More restrictive or less restrictive? Absolutely. More restrictive, so that means we need a higher order filter. Good. So usually what will happen is you'll be given some design constraints. These numbers don't ordinarily get pulled out of a hat. You want to, sort of, you have a signal, you know where the frequency content ends. So you say, I've got a signal, I know that the useful information there ends at 10 kilohertz. So now you have to decide where to put your corner frequency, how much ripple you want. And then the big question is, how big is your transition band? Do you want a really wide transition band? Can you tolerate a wide transition band? And that sort of leads into the next question, which is, what is oversampling? Anyone have a good answer for this? Why would you want to do that? Why would you want to do that? Any guess? I don't mean to pick on you. I'm just...
I have a better picture of the original signal.
Partially. I mean, that's correct. But there's more to it than that. Anyone else? Yeah, why would you want to? It's not to pick up more information. Right. You either get it or you don't. You prevent aliasing, but you were going to prevent aliasing anyway with your filter. Right. We're sort of... Oh, no. You always need the anti-aliasing filter. Right. I mean, you could... We're sort of dancing around the right answer. Okay. So, strictly speaking, does anyone have another guess before I... Exactly. It makes it... It lets you have a filter of less order. That's exactly the right way to say it. So essentially, here's your problem. Let me just scroll up to the top of the page. So let's say you start out with, all right. I'm going to give you a practical example based on something that I've worked with. So I've worked with some neural signals. So here's the frequency. And let's say that you know, there's information. That's actually not quite what it looks like. I'll try to do a little bit more realistic. So let's say this is about, we'll call it, I don't know, 10K, 10 kilohertz. It's kind of hard to write when the screen is flipped up like this. You'll bear with me. Right. So that's 10 kilohertz. So the signal of interest is at 10 kilohertz and below. But you can see clearly that there's information in the signal above 10 kilohertz. And I know this, right, because I've looked at the signal before. I've looked at its frequency content. It's indisputable. There is information above 10 kilohertz, but I don't want that information. I want to get rid of it so I can sample. In reality, that information sort of trails off, you know, pretty far. So it needs to go through some sort of filter. Now, for practical reasons, I don't want to build a 20-order filter, because I'm actually going to build this filter out of resistors and capacitors and op-amps. So there's really a practical limitation to how big I want to build this filter. So what I'm going to do is, actually let me draw it on top of the same axis. So I essentially have two options. So now the black is my signal, the red's going to be my filter. And remember, when you're looking at the frequency domain, I'm going to just do a multiplication of the information in the signal with the filter to get my result. So ideally, what I'd do is I'd build a filter that looked like this. Right? That's the perfect filter, because everything at less than 10 kilohertz remains perfectly as is, and everything above 10 kilohertz completely dies out. And if I do that, my sampling rate can be 20K. But you know what? That red filter is pretty hard to build. You can actually take a pretty good stab at building it in the digital domain if you use a FIR filter. But you're not going to build it in analog. There's simply no combination of devices you're going to build that's going to get you that. You could get pretty close to it if you were going to be willing to build a filter of order 80 or 90 or something crazy that nobody would ever really want to build. So while mathematically that's ideal, practically it's not ideal. So here's what I'm going to do instead. I'm going to build a filter that drops off a little bit slowly. So even though I want it to stop at 10 kilohertz, it's going to still pass some information at beyond 10 kilohertz. But that information, it's going to be there, but it's going to be divided down, you know, by a lot. It's not going to be completely gone, but it'll be divided down. But now, now let's say that there's still sort of relevant information up to about, let's say, 16 kilohertz. Although the information between 10 and 16 has been attenuated. So this got divided. So this has been made smaller. That's almost in English. This has been made smaller. Okay, that doesn't sound quite grammatically correct, but you get the drift. So now I oversample, right? I sample at something like 32 kilohertz. So here's a situation where I oversampled. My signal was at 10 kilohertz. Nyquist says filter and sample at 20K. But that's not really, if I wanted to do that, I'd have to build a filter of a very, very high order. You know, let's say, you know, something like filter order equals, I don't know, 50. But now if I'm willing to oversample, now I can create a filter that's acceptable with a much lower order, say like 4. So yeah, my filter isn't nearly as pretty, but because I'm willing to oversample, I can get away with a much easier to build analog filter. So that's sort of the basic trade-off. You said it perfectly. So what's the flip side of the coin? Why wouldn't I want to oversample by a factor of like 1,000 or 10,000 or something crazy? Because that's the other thing I could do, right? I could make a huge sampling rate, and then my filter basically wouldn't matter, like you suggested. What's the limitation on that? Let's say I can. Let's just argue that it's possible to actually build that, all the circuitry. Why wouldn't I want to do it? Right. Let's say, let me give you a third option. Fs equals 1 gigasample per second. I mean, crazy high, right? Guaranteed to have no aliasing. Why don't I want to do this? It's not even like a mathematical answer. It's just a practical answer. The clocks are costly. That's part of it. The other thing is, what am I going to do with 1 billion samples per second? Right? Now I need a digital processor that's powerful enough to handle 1 billion samples per second. Okay, I might have 30 channels in my system. That's 30 billion samples a second. You know? Exactly. Now I need, if I do the third option, the purple option, now I need a digital processor that's really much more powerful, power hungry, physically larger. I've really increased the burden on the digital processor. So here I have a relatively simple digital processor, right? Whereas here I'm requiring a very complex DSP. So that's essentially the trade-off. And like, you know, we said, of course, now you have clocks that you have to deal with. You have to generate a gigahertz clock. You're going to have to manage data on buses moving that fast. You know, it winds up being you wind up with a much larger and more complicated DSP than you would have had otherwise. So there's such a thing as overkill in this situation. Yeah, exactly. Exactly. Right. I mean, one thing you could do is oversample, create a perfect brick wall digital filter, which you can do, and then downsample back to a more reasonable frequency. But you still have that chunk in the middle that's dealing with that 1 gigasample per second. So, you know, once you have that data, you have to do something with it, and there's a computational cost for that. So it's a trade-off. That's all I'm trying to say, and there often is no right answer. It's just a little bit of common sense as to, you know, what's better and what's worse. All right. Let me jump forward a little bit. So there's 4 kinds of filters that the book talks about. There's Butterworth, Chebyshev, elliptical, and Bessel. So I have question 5, which asks, which one is the best for anti-aliasing? Does anyone have a guess on that one? Right, so there's 4 main kinds of, there's actually more than 4, but the 4 main flavors of analog anti-aliasing filters are Butterworth, elliptic, Chebyshev, and what did I say, Bessel. And the question is, which is best for anti-aliasing? Any thoughts? Okay. Okay, so elliptic gives us low filter order and best transition band. Does that mean it's the best? I agree. It's actually a trick question, right? I put it in there for a reason. There is no best. It totally depends on what you're looking for. So there are, you could easily imagine a situation where the most important thing for you is that you have the simplest possible filter, right? The lowest possible order filter is by far the most important thing. In that case, you might want to think pretty seriously about an elliptic filter. But there are other circumstances where an elliptic filter wouldn't even be close to the best option. So let me just comment real quickly on what some of the other trade-offs were. Actually, are you sure that wasn't Chebyshev? Were you talking about elliptic or Chebyshev for those qualities? I might have them backwards in my notes, but I have some like similar comments, but I had that next to Chebyshev. Okay, Chebyshev 1 and 2. Okay, well, it's probably possible I screwed it up. Okay, in any event, so the book talks briefly about the advantage of the Bessel filter. What does Bessel buy you? And this sort of that's actually connected to one of the other questions. Bessel filters have a really cool quality about them, found in no other filter. Let's see if I can find it in my book. So I think we're going to be on page I don't see it. Well, it's not that big a deal. Type 2 Chebby, elliptic. Yeah, it's actually on page 195 when it's talking about the linear phase approximation. And then about halfway down it says that transfer function is called the Bessel polynomial. These filters are often referred to as Bessel filters. That's at the bottom of the page. So Bessel, this isn't something I necessarily expected you to pick out of the book because it's kind of buried in there, but I'm just passing it on because I believe it's important information. So again, keeping in mind that the whole reason we're going through this is that just to remember that there's pros and cons why you'd want to pick one anti-aliasing filter over another. Bessel has this property which is that it has linear phase. And that was one of the other questions I had on here, which is, let's see, question 4 I said, section 4.6 talks about linear phase being a desirable thing. What is linear phase and why might it be a desirable filter quality? Okay, so no distortion. All right, that's good. No what? Okay, that's more or less the same thing, right? So no distortion, no phase distortion for different frequencies. What does that mean? Same amount of time. That's right. That's absolutely correct, and it's a kind of an important subtlety. So I'm going to sort of beat on this now because we're going to see it again later. We're going to wind up looking at linear digital filters later on, and it's equivalent principle. Mm-hmm.
When I reconstructed the signal, means passing yn through passing Xn through the filter and getting Yn, then I saw that 1 kHz signal has been reconstructed but delayed for some amount. So frequency amounts are delayed for different amount, then the reconstruction has been distorted.
Absolutely right. Let's say the phase function looks like this. So your phase as a function of frequency is equal to some constant times omega. All right, so this is a linear phase. All right, so now I'm going to take some frequency omega 1. Okay, and I'm going to say, so here's a sine wave at frequency omega 1. And I'm going to put it through this linear filter with linear phase. So linear phase filter. And somebody's going to come out the other end. So let's see if we can see what this phase lag is. Well, for this frequency, we know the phase lag is going to be alpha times omega 1 radians. All right. Well, how many seconds does that correspond to? Well, this frequency. So let's see. We're at a frequency of omega 1. So that means in hertz, we're at a frequency of omega 1 over 2 pi. Which means the period is going to be 1 over the frequency, which is going to be 2 pi over omega 1. So that's one whole period is that amount of time, 2 pi over omega 1. Now, if one period corresponds to 2 pi radians, so 2 pi radians corresponds to a time of 2 pi over omega 1. But I don't have 2 pi radians now. I have this many radians, right? That's my linear phase tells me that that's my phase shift. So we'll do a little cross multiply. If 2 pi radians corresponds to a delay of 2 pi over omega 1 seconds, how much delay does alpha times omega 1 radians correspond to? It's just alpha, right? We cross multiply. So, in other words, no matter what the frequency is, your signal always gets shifted by a constant amount. So in other words, if we had this frequency and this frequency and let's pick a dark one and this frequency, then on the far end they would all get shifted by exactly that same amount of time. That's alpha. And that's the beauty of a linear shift. All the frequencies get shifted by the same amount of time. So what happens is we use this buzzword of no distortion, right? So a typical application of this is some signals that I was working with. I was trying to amplify these action potentials that come from from brain cells. And as it turns out, the shape of those, the actual shape of that action potential is very important. And I want to make sure that I preserve the shape of the action potential as it goes through the filter. Well, if I use a Butterworth filter or an elliptic filter, there's no guarantee that after I filter it, that action potential is still going to have the same shape. But if I use a linear phase filter, I have a much better chance that it's going to come out looking exactly the same as when it went in. Now, what's the trade-off? I have to use a much higher order filter to get the same amount of cutoff in a Bessel filter. But in that situation, I was willing to live with that, right? That's a practical, you say, okay, well, I don't care. I'll build a 10th order filter if I have to, but it's absolutely crucial that my signal doesn't change shape. Now, in another signal, in another application, you might not care. You say, oh, sure, you know, phase distortion all day long. I couldn't care less. I'd rather have a sharper filter. Okay, so then you pick something else. You pick a Butterworth or an elliptic or whatever it is. So it's all application dependent. Good? Let me run through a little example. The good news is that MATLAB does all the work. So in the practical aspect of designing this, these things are, it's all stuff that's built into MATLAB. So you just have to tell MATLAB how to design the filter, and it will basically do it for you. And I just wanted to run through an example of that, and I'll put all this code on Blackboard. Alright, so in this problem, I gave myself the task of designing a low-pass Butterworth filter with a cutoff frequency of 1 kilohertz and a stop band that starts at 5 kilohertz. I'm willing to tolerate 3 decibels of ripple in the pass band, and in my stop band, I need everything in this at the stop basically everything at greater than 5 kilohertz should be attenuated by at least 60 decibels. Right? So that means that it should be divided by at least 1,000. Right? 60 decibels corresponds to 1,000. So that means that anything above 5 kilohertz should be divided by at least 1,000. So I'm going to use two, and I want to use a Butterworth filter. So I'm going to use 2 built-in MATLAB functions. The first one is essentially tells you the order of the filter. Okay, so and it's specifically for Butterworth filters. So what I'm going to tell it is the low pass frequency and the high pass frequency, except I have to remember to express them both as radians, not as hertz. MATLAB doesn't do hertz very well. So my F low is 1 kilohertz. My F high is 5 kilohertz. So I tell MATLAB, please create me, or please tell me what order I need that goes from 1 kilohertz to 5 kilohertz. I'm willing to tolerate 3 decibels in the pass band. I need 60 dB of attenuation in the stop band. And then I put this the character S just tells it that I'm creating an analog filter, not a digital one. Okay, so MATLAB goes and it does all the work for me. So let me just tell it to pause there. So now I'm going to run. And with any luck, it tells me my filter order is 5. So I need a 5th order filter. Now, if you read the book, there's like 5 or 6 pages where it derives the formulas to tell you how to come up with the filter order. We don't care. The reason we don't care is that we understand the intuition behind the filter order, right? I know that if I change different parameters, I know that it's going to get bigger or smaller. And I know that MATLAB can actually do the math for me. So the actual theory behind it, in this case, I don't believe is too important. Okay. So now we can actually create the filter. And you sort of have 2 ways you can go about doing it. One is you can compute the zeros and poles, or you can compute